Thomas, thank you. Tomas, Stephen.
Yep, it's me again. So this time is channel sounding has been topical throughout the day. First of all, I want to thank you, Parker, because you've made my life so much easier. I can skip probably half of the presentation now, which is fine because it's the end of the day. So, and it is good as well because then, since you've already explained what channel sounding is, what kind of conditions it works for, and so on, I would be able to focus on the more interesting results and measurements rather than explaining what channel sounding is. All right, so you see there we have the why and applications. These two first bullets, we can probably, and even the third one, we can cover them very, very quickly, and then focus on performance and power and security, which at the end of the day are questions or questions that people are asking about this technology. You know that already. I don't think we need to repeat that. It's a new technology. We had RSSI. We have something now which is better than RSSI, but it's different. And as you explained, it's a complementary technology. RSSI is still there and covers other usages, but channel sounding is focused for this kind of a secure, fine-ranging applications. I'll skip this one. On a very similar slide to the one you had, we see, and we are excited as well about this technology, we see many different applications and that are going to be here. And we agree what we see now and what this technology is going to end up with when we put that in the hands of our developers and customers is something very different, right? We expect that the levels of innovation and that are coming throughout this technology are going to be substantial. So we're really looking forward to this. You also cover this. I'll give a different angle to this. It is a structure, sure, in events and sub-events, but the reason why we did this, at the end of the day, is to allow coexistence. So if you look at how channel sound is structured, when it comes to the overall Bluetooth communication and how the connection intervals work in Bluetooth, channel sounding was developed from the very first day so that we could accommodate the channel sounding events and sub-events within the other activities that the Bluetooth actually is dealing with. For instance, you might have an ACL connection event going on, and then you are able to, or the controller is able to schedule the channel sounding sub-events within those intervals without affecting the main activities from the other connection activities. So that's important. It shows as well that from day one, when we were developing this technology, we had the intention of interleaving in time channel sounding with other activities, and that's of course very important for central devices that maintain multiple connections and maintain not other Bluetooth activities but Wi-Fi or other Bluetooth connections. Okay, so really went through the first three bullets really quickly, which is nice because now the part of the presentation where I wanted to focus is coming now. So we've been working in TI on channel sounding from day one. I was personally involved in the development efforts since the very start, and that was a number of years ago. And internally, of course, we've been working here. So where we stand today at the verge of the final release of the specification is that TI and many other companies do have implementations, and we've been going through the practical problems that channel sounding imposes and how to solve them. So what we want to illustrate here today is three scenarios, line of sight scenarios, where we are measuring with channel sounding these scenarios and the results we see and how the different design options and open to designers would affect the final accuracy. And what levels of battery lifetime, what levels of energy you might be trying to or aiming for with this kind of applications. So these three scenarios, we will start with the RF measurement chamber, then move to the outdoor park. We are based in Oslo, so this is a few weeks ago. Early spring in Oslo is a bit sad, but it will get better. And then the final scenario is our indoor office. I need to say that the measurement chamber is not an anechoic chamber, though it looks like one, but it's not strictly an anechoic chamber. The difference is that we use this chamber for measurements so that we can measure without interference. But that's not the same as measuring without echoes. And it might be a slight technical detail, but it's not, because channel sounding, as in everything in RF, is affected by the multipath propagations. And before I go into more details, I want to use this time to explain, to give an example of how to think about this. So imagine you have a pond of water, still water, and there's a drop coming to this pond of water. You'll see that every time the drop hits the water, there will be waves propagating from the water, right? From the drop. And eventually, once those waves hit the borders of that pond, we start reflecting back. Since we have a continuous source of drops, then eventually you'll get to a standing wave. But the important point here is that every single spatial point in the pond is going to be affected differently, right? And just by moving a few centimeters around that spatial point, the combination of the waves is going to be different. That is exactly what's happening. It's actually very similar because the wavelengths of those signals are actually similar in a few centimeters, but in 3D space. You have a source of RF signals, say one of the transmitters, that is injecting those RF signals to the channel, and those signals will travel directly to the line of sight, to the receiver, but those same signals will expand through the overall channel you are measuring and eventually combine differently in each 3D point in space. So what happens here, and that's all the introduction, this is important because the fact that, as you mentioned, multiple antenna paths help here, or multiple antennas help, is that each of these antennas is providing a diversity or providing a point in space that is slightly different from the other ones. And even a few centimeters of separations matter here. Okay, that's the kind of RF course background to everything I'm going to say. Just one more slide to illustrate how we're measuring things. We're using, of course, our evaluation boards at both sides. This is something you can just buy from the TI shop. You put two together. There's a multiple antenna board attached to those devices. You could see that in the previous pictures. And then the configuration is the typical configuration for channels. I mean, there is one initiator and one reflector. They are stationary. And we were measuring 20 different measurements or repetitions per distance. And then there are, just to illustrate the differences, we were measuring for one single antenna path and for 4 antenna paths. And those 4 antenna paths, and listen to what I'm saying here, I'm not using the word antenna, but the word antenna path. That's important because this is also baked into the specification. What happens is that you can have 2 antennas at each end. And these 2 antennas would create 4 different combination of paths from antenna 1 to 1, 2, antenna 2 to 1 and 2. So, and that's what it's important, not the actual number of antennas, but the actual number of antenna paths that is created by the physical antennas. So in other words, you don't need to have 4 antennas at one of the ends. You can only use 2 if you want to. And as explained before, you don't need to even. If you can use this technology with one single antenna path if you want. Phase-based ranging uses the fact that, as I explained as well, you need to measure multiple tones and combine those tones together to obtain the final distance. And how you combine those tones, that's a very important topic. That's what is called the CS post-processing. In channel sounding, post-processing is not part of the standard. That's part of the innovation of channel sounding, what's left for different implementations to play with. Similar, for instance, to things like channel selection, not channel selection, but channel classification algorithms in Bluetooth. Here, different implementers might use different ways of combining that information, and it does make a difference. And just to explain the differences, we will use two different algorithms here. The simplest one is the one that was explained in some of the slides. I think the ones from Rodesarts, where you have the simple equations. This is a very simple linear regression equation. But there are more advanced algorithms called super resolution algorithms or multiple signal classification. That's the acronym for music, where they are much better in order to figure out the complexities of the channel. They can distinguish all the different paths of the signal much better. Of course, as everything in life, if you want more, you need to pay more. So super resolution complex or music algorithms would require significantly more processing power from the end nodes. But the choices are there. So the flexibility is it's again flexibility. The specification would allow all kind of implementations here. So let's start with these plots now. What we wanted to illustrate here with these plots is how significant multiple antenna paths can be, even in conditions where apparently it should be good enough. This is the line of sight condition in the RF measurement chamber, right? What you see here is the error for 1 meter is almost nothing, but then for 1.5 meters and 2 meters, we had even 1 meter of error. Now, this plot is made like that on purpose, because we were trying to find the worst possible condition, but it is also illustrating that those worst possible conditions actually exist. And going back to the pond, you might find a position where the waves are combining in such a way that it's just impossible. So if you have one single observation point, these conditions can occur. However, once you immediately go into multiple antennas, that's resolved, because you would have, or the device would have enough observations to figure out what the best of those are. Also, I need to illustrate that this is using the simplest way, the simplest algorithm, which combined to this shows that the simplest algorithm with one antenna path might fail. In many cases might fail with a lot of error. But then a lot of error, it's 1 meter of error, so it's not that bad. It's not 20 meters, it's 1 meter of error. So for some applications, going in this direction is good enough. Okay, so let's go into more advanced setups, the line of sight outdoors park conditions. So what we see here is first these plots there are the single antenna path, but in this case, since we are outside, we are in the real world, we used already the super resolution or complex algorithms in music. So by using music and using one single antenna path, we're getting results that are, in this case, it's summarized there, within 60 centimeters. And when I say within 60 centimeters, it means that 90% of the measurements were having the correct answer in 90% of the cases. Right? If we then move to multiple antennas, then the error decreases significantly, and the overall accuracy becomes less than 17 centimeters up to 6 meters. And that's quite okay. It's under 20 centimeters for up to 6 meters. That's what we measured there. with 4 antenna paths and super resolution algorithms. That's okay. Now, in more kind of challenging scenarios, this was our office. Now we took these measurements just to try to illustrate a common scenario where people were moving around, where you have computers, and this is just our normal working day, right? Single antenna path more versus 4 antenna paths. And you can see here is, of course, again, the same theme. 4 antenna paths helps. It is more challenging, but still we are also going up all the way up to 15 meters in this case. But up to there, even the 12 meters was very good. The overall cumulative distribution function for all the different measurements with 4 antenna paths and super resolution algorithms was still within 60 centimeters, up to 50 meters indoor office conditions. I think that's a good result for this technology. Okay, so we've established now that accuracy in terms of distance estimation is good enough, and also it's also something that you can modulate with different conditions. You can modulate with the algorithms, and you can modulate it with the number of antenna paths. So what are the aspects of latency, energy consumption of those modulation options? What we're going to play with now is number of tones. Again, we're using 72, but you can reduce that even further to, say, 40. We can play with number of antenna paths. We can play with the parameters and timing and configurations, and you can play with security. Probably going to skip this one since we've already covered in multiple previous presentations of how this works and what mode zeros are and mode twos. You might not be able to remember it now, but this is how the underlying mechanisms of channel sounding operate. What we are going to introduce here, though, is the fact that since we see the need for complex algorithms, what TIA has done is to incorporate a mathematical coprocessor in our devices. So this coprocessor will take the burden of the complex calculations inside the device, so that you don't need to send the partial samples outside to an external device or anything like that. Or you don't need to do that in the main CPU, because that also would use more energy. So this plot here will illustrate how latency in general works. Let's start with the upper section here. What we see here is a channel sounding procedure with using mode zeros and mode twos, 72 of them, that completes in 16 milliseconds. And using an energy we've measured out of 520 microjoules. That's the actual measuring part. That's where all these RF frequencies are being sent and received and computed basically inside the device. The information gathering part. Then we have a second part, which is what we call the phase measurement transfer. So what happens here is that we have the initiator and we have the reflector, and the reflector is sending back the local measurements to the initiator, so that the initiator can combine his own local measurements with whatever is coming from the reflector in order to do the algorithms. And that's also part of the overall scheme here. So we need to account for that. But that's rather quick, under 4 milliseconds, and it uses about 64 microjoules of energy. So if you notice here, these two parts are identical now, because that's basically the same thing. The only difference is how you parse the results, the raw data from the measurements, how those algorithms. So if you were to implement music on an ARM Cortex M33 running on 96 megahertz, there's a heavy calculation. It's a heavy calculation. It might use between 400 and 600 milliseconds. So it's significantly longer, and those plots are not to scale by any means. So it's a very heavy calculation and will burn a lot of energy. So we don't see this as being an alternative. The only way of actually having a local measurement computed on the device is having an accelerator. So that's why we added, and it's not only TI, we see many other companies doing similar things. So by doing that, the overall post-processing would reduce to 15 milliseconds, and the energy would be less than the actual calculations. But the total amount of latency is, for this particular setup, is 35 milliseconds, and the energy just below 900 microjoules. So 35 that's less than 40, so it means that you could essentially measure 25 times per second your distance. So if you have that ability, of course, once you open that, you have not only the ability to measure once, but multiple times within 1 second, and do any kind of post-processing of the distances as you would like to, per node. Just to get one more step further, of course, that would be for, I think it was one antenna path here, yeah. So if you add more antenna paths, the duration will increase. Also, the post-processing might increase. Here, that's a section where TI and many other companies are experimenting. These are the stupid way of doing things would be run music per antenna path. There might be, or there certainly are, better ways of doing that. But if you were to take the naive approach where you run music per antenna path, then the overall scaling of energy or latency and energy would follow those curves, which again illustrate that there are multiple options here in channel sounding. You might go for applications that require very coarse accuracy and have a very tight energy budget, and you can go in this direction there, or you can go in the other way, like applications that require extreme precision and don't have any energy constraints, then you can go for all the other direction. But all those things are part of the spec. So the freedom and the liberty to play and experiment with that is there. Okay, and finally, it's one single slide. This is very important though. I'll try to cover this as much as possible in a way that is understandable, but we've spent years on the security aspect. Security has been a concern from day one for channel sounding. Security is the reason why RTT was added to the specification. It's not only phase-based ranging, it's also RTT. Those two, as it was mentioned by Parker as well, the RTT and the PVR measurements can be intertwined and they shall be consistent. That's part of the security. If you're measuring the distance through PVR and you're measuring the distance through RTT, whatever you get shall be the same. If there's an attack on PVR, there has to be a similar attack on RTT, and both attacks need to align properly. If they don't, there's a way of detecting a security breach. And getting an attack on both RTT and PVR simultaneously that actually align is not trivial. Beyond that, if we've protected the RTT significantly, so here, if you're kind of familiar with the man-in-the-middle attacks terminology, where you have Alice and Bob being the legit part of the communication. If there's an attacker in between Alice and Bob, what happens here is, let's go follow first the blue lines. Alice is transmitting his signal. The signal, if there is no attacker, will propagate through the channel, which is represented here by H normal channel, which is a normal delay channel with a multipath and propagation and attenuation, and then Bob will receive that signal. It is a known signal because both Alice and Bob are cryptographically deriving the same sequence of bits. So both Alice and Bob are aligned to whatever they are going to transmit and receive. They know everything in advance, right? And they can, once Bob is receiving the signal from Alice, Bob will figure out, okay, this is matching, and the delay of the channel is whatever it is, and that's the RTT, so that's the distance. That's the normal communication way, that's the normal propagation way, and that's the normal operation way. However, if there is an attacker in between, that attacker might manipulate directly the bits that are traveling through the air. The attacker cannot know in advance those bits because those are protected, those are cryptographically protected and not known for the attacker. Those are also generated randomly per RTT event. So the attacker just needs to guess what those bits are. But in order to guess, he has to analyze the signal. And in order to analyze the signal, there will be a certain delay to that analysis. And in order to eventually manipulate the signal, that manipulation, if you add everything together, will leave an imprint on the manipulated signal, on the actual physical RF signal. That imprint is something that can be detected. That's the NADAM that also was mentioned by Parker. NADAM is a normalized attack detector metric that is part of the standard that basically tells you if you are interested in security, there is something that is going to look and examine the signal. And it's going to make sure that whatever gets here is and looks like the real signal and is able to detect otherwise any manipulations. That's the way to achieve security. And we've done, not only TI, but all the member companies in the SIG have done a very significant number of investment in this kind of a technology. So we're pretty sure that this is secure. So again, if you combine RTT, PVR, NADM, and all the bells and whistles we put in here, we can ensure that phase-based ranging or Bluetooth channel sounding plus RTT is a secure technology for distance measurement. So that's I'm actually running right on time. Just to summarize, we have a new technology. This is going to enable high accuracy and low cost and secure ranging by design. The good thing here is that first, we have multiple options. We have multiple antenna paths. We have multiple algorithms we can employ. We can scale up and down these kind of solutions according to the number of tones, according to the different applications. We do see, though that an integral part of channel soundings are the algorithms, and those are going to be catered by in the solutions as well by the silicon manufacturers. And eventually, we believe strongly, and there's no proof otherwise, that this is secure technology. So with this, both from Scilabs, from TI, from NXP, from member companies, we are all very excited about the channel sounding, and we are just eager to get out, and I guess the Bluetooth SIG as well, to get this out in the market and see what people can do with this technology. Okay, thank you. That's it.
And now questions for Tomas, Parker,